Greetings, everyone. My name is Hloniphile, and I'm going to be covering the probability for grade 10. So, to slide up, but it doesn't allow me. Not too sure if it's the sharing or.
Oh, right now we can see the front page of your slide. Okay, yeah. Yeah, we can.
Okay,
Yes.
thank you. So we're going to start off with a few definitions on probability. So an experiment, what do you mean by an experiment in probability? So an experiment refers to uncertain process. An experiment refers to uncertain process and the outcome. The outcome of an experiment is a single result. For example, let's say we are having a coin toss. So the coin, let's say, is tossed, and it lands say either heads which we're going to represent by 8 or tails. Right. Facing up. Right. So this is an example of an experiment. So an outcome is a single result. So an outcome of this coin toss will be coin lands, let's say, with heads facing up. Right. So an example of an experiment is a coin toss, and it could either land heads or tails facing up. So an outcome is a single result of this experiment. So the results would be the coin lands heads facing up. So a sample space, what do we mean by a sample space? So a sample space of an experiment is a set of all possible outcomes of that experiment. Is a set of all possible outcomes. Let's say the sample space for this experiment, the sample space, we can call it S. The sample space is a set. So this is a set. So it could either land heads or tails up, which means it could either be heads or tails up. So this is a sample space. And we have a sample size. So we have a size of a sample space, we represent it's the size of a sample space by n of s. N of s would be, okay, we have this outcome as well as the second outcome, which means in total we have 2 outcomes. So it's the sample size. So an event, what do we mean by an event? So an event is a specific set of outcomes of an experiment that you are interested in. Let's say we are interested in heads facing up. Let's say we are interested in heads facing up. So which means our event is going to be heads. We are only interested in heads facing up. So the set of this event is going to be 8, right? So, but the size is going to be n of e. The size of this event is going to be 1 because we are only interested in heads facing up. So what do we mean by a probability? So a probability is a real number between 0 and 1. And probability can be described in 3 ways. So it's either we can use the real numbers between 0 and 1. Like real numbers like 0.5, 0.7 up until 1. It's a scale from 0 to 1. So this is the probability scale. And let's say, for example, real numbers, let's say, let's take 0.75. Let's take 0.75 as our example. So we can represent this 0.75 as a real number, right? And we can also represent it as a percentage, like multiply this by hundreds, right? So which means this could be 75%. Or we can represent the probability by a fraction. 0.75 is 3/4. But we do have a formula for probability, for calculating the probability. So remember, there's the probability is a number between 0 and 1. Let's describe how likely an event, So let's take our examples from the experiment. Let's take our example from an experiment. Let's say we're looking for the probability of this event from our experiment. So which means we're going to have the probability of this event occurring. So P of E is going to be the size of an event over the size of the whole sample space. This is the formula for calculating the occurrence of this event. So which means the size of the event was 1, right? So which means we're going to have 1 over here, and the size of this whole sample space is going to be 2. So this is the probability of this event occurring. We can take another example, but I'm not sure if we do have time. So let's take a look at example 1. Example 1 says a 6-sided die is rolled. Okay, so which means we have a 6-sided die. So we can call it S, the sample space. So which means we have possibilities of, like we have 6 possibilities. We have 1, 2, 3, 4, 5, 6. So this is the whole sample space, right? So what is the probability that it lands on an even? So on an even number, which means our event, we are looking for the even numbers only. So let's call it our E. So the event, we are looking at the even numbers. So the even number over here is going to be 2, it's going to be 4, it's going to be 6. So which means you can select 2, 4, and 6. So the size of this sample space is going to be 1, 2, 3, 4, 5, 6, right? Which means the size is going to be 6. And the size of this event, is going to be 1, 2, 3, which means we have 3. So the probability that it lands on an even number, which means it's going to be the probability of this event occurring. So which means it's going to be the size of this event over the size of the sample space. So which means it's going to be 3/6. So which means it's going to be 1/2. You must always simplify over here. If you leave it as 3/6, you will not get the total, the full marks. So let's take a look at example 2. Example 2 says a coin is tossed twice, right? And what is the probability of getting heads twice? The coin is tossed twice, which means our sample space is going to be, okay, since the coin is tossed twice, which means we can have heads and heads, right? And we can have heads and tail, and we can have tails and heads, and we can have tails and tails, right? This is our sample space. So what is the probability of getting heads twice? Which means our event, we are only interested in getting heads twice, which means we are only interested in this part over here. So which means we are only interested in this part over here. So the size of this sample space is going to be 1, 2, 3, and 4, which means the size is going to be 4. Then the size of this event, is going to be 1. It's going to be 1. Then we can use the formula. The probability of getting heads twice is going to be the size of an event over the size of the sample space, which means you can have 1/4. You can write 1/4, or you can write 0.25, or you can write 25%. It's still the same, but you must choose one. I hope everyone is still with me. So let's take a look at, okay, thanks. So let's take a look at the relative frequency of an event. The relative frequency, when an experiment is repeated many times, so the number of times a certain event takes place is called frequency. When it's divided by the number of times the experiment was repeated, the result is called the relative frequency. So what do we mean by that? Okay, but you must take notes of this part over here. When the experiment is repeated many times, so the relative frequency should eventually approach the calculated or the theoretical probability. What is the theoretical probability? The theoretical probability is the probability that we calculate, let's say calculate it over here. The theoretical probability over here is 1/4. So let's take a look at example 3. Example 3. Okay. What do I mean by theoretical probability? Let's say we are tossing a coin. I'm trying to emphasize on this part. Let's say we are tossing a coin, then just one coin. So a sample space would be heads and tail, right? Would be heads and tail. So the theoretical probability of getting heads, which means it's going to be 1/2, right? It's going to be 50% chances. So this is what I mean by the theoretical probability. So example 3 says a coin is tossed 100,000 times. Then a coin lands on heads 49,996 times. Calculate the relative frequency. So which means we're going to be using this formula over here. So which means our relative frequency is going to be the frequency of an event. The frequency of an event divided by the total number of times experiment is repeated. Right, this is just a formula. So which means we're going to take our frequency. We've been given the frequency, so which means it's going to be 49,996 over the total number of times. So this is the total number of times. So which means it's going to be 100,000. Right. So this is going to give us 0.49996. So let's calculate the theoretical. What about the theoretical probability? The theoretical probability, since a coin only has heads and tails, which means the theoretical probability over here is going to be 1/2, which means it's 0.5. And 0.5 is much closer to this. This is basically 0.5. It's much closer to this. So the question was saying, calculate the relative frequency of this event and establish whether it approximates the theoretical probability. So let's take a look at example 4. Example 4 says a die is rolled 12,000 times. Approximate how many times do you expect the die to land on a factor of 6. So let's first write the outcomes of this die. So the outcomes is going to be either 1, 2, 3, 4, 5, 6, right? So the factors of 6. So this is our event. So the factors of 6 are going to be 1 is a factor of 6, and 2 is a factor of 6, as well as 3 is a factor of 6, and 6 is a factor of 6. Factors of a number are a number that can divide that number, like number 6, without a remainder. So 1 divides 6, 2 divides 6 without a remainder, 3 divides 6 without a remainder. So these are only factors of 6, right? So let's try and calculate the theoretical probability. So the theoretical probability is going to be, okay, so the size over here is going to be 6, right? Then the size of an event over here is going to be 1, 2, 3, 4. It's going to be 4. So which means the theoretical probability is going to be 4/6. So which means it's going to be 2/3. This is just the theoretical. So let's try and calculate the relative frequency. So the relative frequency is going to be the frequency divided by the number of repetitions. The number of repetitions. Right. So currently we don't have the frequency, right? But we do have the number of repetitions because we've been given in the statement, we've been given. So which means over here, instead of frequency, we currently don't have a frequency, but we do have 12,000 over here. Then this should approximate the theoretical probability. This should approximate, which means this should approximate 2/3, right? So which means we can just solve for f over here, which means we multiply by 12,000 on both sides, which means we have 2 times 12,000 over 3, right? So which means we're gonna have approximate 8,000. So our frequency is gonna approximate 8,000. Okay. So let's continue to example 5. Let's continue to example 5. So example 5 says the letters of the word excellence are written on different cards and placed in a box. So number A says determine the probability of taking out at random the letter E. Okay, so for A over here, the probability of taking out at random the letter E. So which means our sample space has E, has X, has C, has E again, has double L, has E, and CE. Right. This is our sample space. and the size of our sample space is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to be 10. So we are interested in E. So our event is E. So we are interested in E. So we have E over here. We have another E over here. We have another E over here. We have another E over here. So this is our event. That's it. And the size of this event, which means it's going to be 1, 2, 3, 4, right? It's going to be 4. Right. So the probability of getting this event, which means the probability of E occurring, is going to be the size of E over the size of the sample space, which means we're going to have 4 over 10, which means we're going to have 2 over 5. This is the probability of getting the letter E. So for B says determine the probability of taking out at random the letter X or C, the letter X or C. So the letter X, this is our letter X, okay. This is our letter X, and this is our letter C. This is our letter C. So the probability, I'm going to write over here. I'm going to write over here, our B. So the probability of getting X or C, which means the probability of getting X is going to be 1 over 10, right? And the probability of getting C is going to be 2 over 10, which means the probability of getting X or C, which means it's going to be the sum of these, which means it's going to be 3 over 10. Okay, so let's move on to number C. Number C is saying, suppose that the letter N is taken out of the box and not placed back into the box. What is the probability of now taking out the letter E? So which means the letter N is not included over here, which means the letter N is not included, right, in our sample space, which means the letter N is not included on our sample space, which means our sample space now has 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 9, which means the probability of getting E, which means it's still going to be 1, 2, 3, 4, still going to be 4, but over our sample space has changed now, it's 9. So which means it's going to have to be 4 over 9. This is C. I hope everyone is still following. Okay, so let's move on. Let's move on to the probability in terms of sets. So in terms of the Venn diagram. So we use the special diagram called the Venn diagram to represent events in a sample space. So the sample space is represented by a rectangle and the events by cycles inside the rectangle. There are 3 types of Venn diagrams. Okay, so the sample space is going to be represented by a rectangle. We call this the sample space, the rectangle. Then the events that we are interested in, we're going to call them, we normally write them in cycles. So the Venn diagram showing, there are 3 types of Venn diagrams. Okay, so the Venn diagram showing the actual outcomes. For example, let's just move on to example 6 so that you can understand better by these 1, 2, and 3. So let's say a die is rolled, right? So let's A be an event in which the die lands on an even number. Draw a diagram showing the outcomes. So which means we're starting with A, showing the outcome. So the actual outcomes. So this is the sample space. This is S. Normally represent it with a rectangle and the events over here. The events of the outcomes. So we are looking for the even numbers. So we are looking for the even numbers. So a die, remember, a die has right, has 6 sides. So we are looking at the even numbers. So the even numbers would be 2, 4, 6. So this is our A, this is our event, this is our event. Then we still have 1 over here, we still have 3 over here, we still have 5. So we're only interested in A. Our A has to have 2, 4, 6, has to have even numbers. So that's how we represent the outcomes. So let's try and represent the number of outcomes. The number of outcomes, it's more or less like the size of the outcomes. So which means we have A over here. So the size is going to be 1, 2, 3, right? So which means we're going to have 3 over here. We're going to have 3 events. But over here we have 1, 2, 3 again, which means over here we're going to have 3 again. So we can represent again in terms of the probabilities. The probabilities, again, this is our sample space. This is our sample space. This is our event over here. A is an event. So over here, since this we have three, which means in total we have 6, right? So which means the probability of A occurring, our event occurring, is 1/2. We've already calculated this, I think, on example 1, which means over here we have 1/2, and over here we have 1/2 again, or 0.5. We can represent it in a Venn diagram using this method. Okay, so let's move on to example 7. So example 7 says the letters of the word English are written on cards and placed in a hat. One card is drawn randomly. Let A be an event in which the consonant is drawn. So number A says draw a Venn diagram showing all the outcomes. So this is our sample space. We are looking for the outcome. So the letters of the word English are written. Okay, we are looking for the consonant. Okay, so which means this is out since we are looking for the consonant, and this is out, which means we are looking for N, we are looking for G, we are looking for L, we are looking for S, we are looking for H. But we have to include E on the sample space. E is outside our event. So this is our A. So E is going to be here, and we still have I for the word English, right? So for A, that's how we draw our Venn diagram for the outcomes. So number B says, write down the outcomes of the sample space. Write down the outcomes of the sample space and event A in a set form. Okay, so S in a set form will be the word English, E-N, G-L, I-S, and H. The outcomes of the sample space and the outcomes of an event. So we are only looking for N and G and L, S, and H. We are only looking for this, right? So our B writes down the outcomes. We already written them. Then for C says writes down the size of A. So the size over here is going to be 1, 2, 3, 4, 5, which means it's 5. Then the size over here is going to be 2, 4, 6, 7. It's going to be 7. So calculate the probability of A occurring. So the probability of A occurring is going to be the size of an event, right? So our event is A over the size of the sample space. So which means it's going to be 5 over 7. Okay. Let's take a look at example 8. Example 8. Let's say we have a 12-sided die. 12-sided die is rolled. The following events are defined. So the sample space over here is going to be 12 outcomes, right? It's going to be 1, 2, 3, 4, up until 12. Right, the outcomes. So our A, multiples of 3, which means it's going to be 3, it's going to be 6, it's going to be 9, it's going to be 12. Multiples of 3, which means we have 3, we have 6, we have 9, and we have 12. These are multiples of 3. Then our B is going to be the factors of 9, the numbers that can divide 9 without a remainder. So 1 divides 9. So which means we're going to have 1, and we're going to have 3, and we're going to have 9. Right. So the multiples of 5 for C, we have the multiples of 5. The multiples of 5 are going to be 5, and we're going to have 10 over here. So this is our A, B, and C. So let's take a look at the question. It says list the outcomes in a set form, which means this is the first part in a set form. The outcomes in a set form. Then draw a Venn diagram to represent these events. Okay. Draw a Venn diagram to represent these events. This is the sets. Okay. So these they meet as 3. A and B meet as 3, which means they do intersect. So this is our A, this is our B. They meet at 3. So instead of A, we're gonna have 3, we're gonna have 6, we're gonna have 9, we're gonna have 12. There's no need to include 3 again because it's already here. It's already here. So for event B, it's 1, 3, 9. We already have 3 in this part, so which means we're gonna have 1 and 9. Right. So for C could be somewhere over here. This is the event C. It says 5 as well as 10. Right. So, but the whole set has 1. Okay, we already have 1. It says 2. Over here, we still have 2. It says 3. We already have 3. It says 4, which means we can write 4 down. It says 5. We already have 5. It says 6. We already have 6. It says 7. We can write 7 down. It says 8. We can write 8 down. It says 9. We already have 9. It says 10. We already have 10. It says 11. We already have 12. So this is how we draw the Venn diagram. And then for number C says determine the probability of A occurring. determine the probability of A occurring, which means it's going to be the size of A over the size of the sample space. Right. So the size of A is going to be 1, 2, 3, 4, right? Which means we have 4 over here over the whole sample space, which means over 12, which means we have 1 over 4, 8, 12, 1 over 3. So the probability of getting B over here, which means we're going to have the size again of the event B, of which is 1, 2, 3, which means it's 3 over the whole sample space, which means 3 over 12, which is going to be 1 over 4. Then the probability of getting C, which means it's going to be 2 over 12, which means it's 1 over 6. I hope everyone is still following. So let's move on to derived events. So derived events, so we have the complement of an event. What do you mean by the complement of an event? So let's say over here, this is our sample space. So this is our event. So the complement of an event is an event that is not occurring in A. The complement of an event A is an event consisting of all outcomes that are in the sample space, but not in A, which means this will be the complement. Everything else except in A. Everything else except in A. This is called the complement. And we normally write complement as A, something like this. In other books, it's written A. It still means the same thing, the complement of A. What's not in A? Everything else, but not in A. So the intersection of events, what do we mean by the intersection of events? Let's say we have events A and B. We have events A and B. So the intersection, this is A, this is B, is where they meet. The intersection is where they meet. They will meet over here. Is where they intersect. Is where they intersect. So we normally write A and B, or we normally write A intersects. This means intersects B. A intersects B. So what do we mean by union? Union of events. Let's say over here, you have a sample space and we have A and we have B over here. This is A and this is B. So a union is everything that is in A and everything that is in B. We include everything. So everything that is in A over here and everything that is in B. So we will include this part. We include everything that is in A and everything that is in B. So it's normally written, it's A union B. Everything that is in A and everything that is in B. Okay, so let's take a look at example 9. Example 9 says, in a certain experiment, the sample space is, okay, A, B up until H. So events A and B are defined as follows. So the question is saying that represent all the outcomes in a Venn diagram. Represent all the outcomes in a Venn diagram. So let's say this is our sample space and this is A and this is B. This is A and this is B. So A has A, B, C, D, but they overlap. A has D and E, and B also has D and E. So which means D is going to be here and E because they overlap. D is in A, DE, as well as it's in E. So that's why I wrote them over here. So, but A also has A, B, and C. And B has F, G, and H. Right. So represent all the outcomes in your Venn diagram. So this is the solution. Then for B says list the outcomes in. Okay, so let's start with this part. Not A. Not A means the complement. Not A means what's not in A, the complement of A. So which means the complement of A over here, what's not in A, which means everything else that is not in A, everything else that is not in A. So what's not in A over here is going to be F, G, and H. What's not in A. Then number 2 says A and B, which means we are looking for the intersection where they intersect, A and B, where they meet. So over here, you can say A intersects B, where they meet. So which means they meet only over here, which means we're gonna have D and E. We're gonna have something like this where they intersect. And for number 3, we're looking for A or B. This means A union B, which means everything that is in A and everything that is in B. We include everything if it's all, everything. So which means we have A, B, C, we have A, B, C, and we also have D, E, we also have F, G, H. So this is what we have. So A union B is going to give us something like this. I hope everyone is still following. So let's move on to number C. So number C says, what is the value of N, which means we're looking for the size, and we're looking for the size of complement A, not in A. We're looking for the size of the complement A. So the size of the complement A is going to be 1, 2, 3, because we've already calculated the complement A. So we are only now looking for the size, which means the size is going to be 3, right? So over here, we're looking for the size of A and B. A intersects B, which means the size of A intersects B, which means we're going to have 2 because we have D and E, which means over here, we're looking for the size of A intersects B, of which is going to be 2. The size over here, we're looking for the size of A union B. A union B, which means it's going to be 3, it's going to be 6, 7, 8, which means we're going to have 8 over here. Okay, so let's move on to D. So D is saying determine the size, not A intersects B. Not A intersects B. This means that we're looking for the size of A complement intersects B. Right. So let's start by looking at A complement intersects B. Let's start by looking at this part over here before looking for the size. So what's not in A? What's not in A? What's not in A is F, G, and H. What's not in A is F, G, and H, right? So where they meet, which means the intersection of what's not in A, it intersects with B, which means the intersection will occur over here. The intersection will occur over here. The intersection, which means it will occur on F, G, as well as H. The intersection is going to be something like this, because we're looking for something. This is our A, guys, and this is our B, right? So what's not in A is going to be something like this, right? What's not in A is going to be something like this. It intersects with what is in B. So what's in B is going to be this part over here. So which means we are only interested in this part. We are only interested in this part, which is going to be F, G, and H. So the size over here, the size of A complement intersects B, which means it's going to be 3. The size is going to be 3. So what about the probability? What about the probability? So the probability of A complement which intersects B is going to be this 3 over here. It's going to be 3 over the sample space, 3 over 8. So this is our probability. So let's take a look at example 3. So we're looking for, okay. I'm sorry, I'm gonna have to take this out. Okay, so we are over here now, number 3. So we are looking for the size of complement A. Okay, so I made a mistake over here. It's supposed to be O. It's supposed to be O. So it's supposed to be a union B. Right. So let's take a look first at this part, not the size, the set. Let's take a look at the sets. So what's not in A? What's not in A is going to be F, G, and H, right? What's not in A is going to be F, G, and H. What's not in A? This part over here. We are including everything that is in B. We are including everything that is in B, which means everything that is in B, which means it's going to be F, G, H, as well as D, as well as E. Right. Since union includes everything, which means this is the set that we have. So which means the size of this set over here, the size of this set is going to be 1, 2, 3, 4, 5, which means it's going to be 5. Right. So this is the solution for number 3 over here. So let's take a look at number 4 over here. So we are looking for the probability. We are looking for the probability of complement A, union B. So which means the probability over here is going to be 5 over the sample space, 5 over 8. So this is the solution for number 4. So for number 5 and number 6, I'm sure you guys are gonna be okay. Or if you still need me to explain number 5 and number 6, I can do that. Mr. Duazan?
Yes, Nomfundo.
Are
Oh,
there any questions, or must I continue do number 5 and number 6? Because number 5 and number 6 is more or less the same as 1, 2, 3, 4.
Oh, you can just do number 5 while we're waiting for our next presenter.
Oh, okay, okay. Okay, so number 5, we are looking for the probability. It's supposed to be capital letter P over here. The probability of complement A. Complement A, what's not in A? Or, which means union. Or, what's not in B, which means complement of B. Right, so let's first find the sets of this part over here. Let's first find the sets of this part. So what's not in A? So what's not in A? What's not in A is going to be F, G, and H. It's going to be F, G, and H. And what's not in B? What's not in B is A, B, and C. So remember this is a union. So we are including everything. We are including what's not in A. We are including what's not in B. So which means the size over here of what's not in B, union, what's not in A, union, what's not in B, which means it's going to be 1, 2, 3, 4, 5, 6, which means the size is going to be 6, right? So which means the probability over here is going to be 6 over 8, of which is going to be 3 over 4. Right. So let's try and do number 6. Number 6. So what's not in A? What's not in A? We are looking for the intersection now. So what's not in A intersects with what's not in B. So we're looking for this part. So what's not in A? What's not in A is going to be F, G, and H. What's not in A is going to be F, G, and H. And what's not in B? What's not in B is going to be A, B, C. Can you guys see this? They do not intersect. They do not intersect because over here, this is our A and this is our B, right? So let's start with what not in A, which means it's going to be this part over here. What's not in A? This is what's not in A. And this is what's not in B. This is what's not in B. So we're interested in the point of intersection. So they don't intersect. In fact, they intersect over here, over on an empty space. They intersect only over here. They intersect only over here. So they don't intersect. So we normally write an empty space if they don't intersect, or we normally write something like this. Something like this means an empty space. So the probability of this part, which means it's going to be 0 over 8. So they will never intersect. So which means the probability of them intersecting is going to be 0.
All right. Thank you so much, Miss Kabuz. That was a beautiful presentation. So if you have any questions, you can type it on the chat box or maybe send us an email. Then we'll escalate it to Ms. Kabuza. She'll answer you, or one of us will answer you. So at 12, don't forget we have lucky draws. So if you want to win something, please come back at 12. Right now we'll have a lesson on grade 11. We'll have Mr. Nkosi. So Mr. Nkosi has been teaching for years. He's also a data analyst. And Mr. Nkosi, I'm not sure if you can hear me or you're in the meeting. In the meeting. Oh yes, I think you'll have more time. You'll have more time. So you'll have more time today to go through your lesson and may you please share your screen. May you please share your screen. Mr. Nkosi, are you winning with sharing your screen?
Mr. Nkosi, are you still with us? It seems like Mr.
It
Nkosi
seems like Mr. Nkos
is having some
is having some
internet connection problems.
connection problems.
I think he's still in the building.
facilitators. My name is Nkosi. I will be taking you through probability for grade 11. Okay, what we are going to be looking at in this lesson, we are going to be reviewing the definition of probability, review some set theory and Venn diagrams, use Venn diagrams to solve probability problems, decide whether events are mutually exclusive or the other. Now, you remember that in grade 11, sorry, grade 10, they told you that the definition of probability, so that we are looking at the likelihood of an event to happen or not to happen, because some they are just taking it in one direction, like we are always looking at the likelihood of an event to happen, but also we can look at the likelihood of the event not to happen. So here, the probability of an event occurring is equaling the number of elements in an event over the number of possible elements. So this is the terminology that you guys learned in grade 11, where N of S, we are looking at the number of elements in the sample space, and the probability of S, that S there, it represents the sample space. So the probability of the sample space must always be equal to 1. So N of A, the number of elements in an event A. So now what could be the probability of A? The probability of A, we can say the probability of A is equaling the number of elements in A over the number of elements in the sample space. Sometimes you will see this A prime in your questioning. When they question you, they'll say, find the probability of A prime. In other words, they are telling you that this means not A. So you are finding the probability of not A. So of which is the opposite of A. So N of A prime means that a number of elements not in A. So now we have this guiding formulae. So this formula means what? It says the probability of A plus the probability of not A is equal to the probability of the sample space. So the sample space would be the probability of A plus the probability of not in A is equal to that probability of the sample space, which must always gives you 1. If you get your answer that is not 1, there is something wrong with your with your calculations. Now, the probability of not A will be the probability, it will be 1 minus the probability of A. Okay, let me just switch on my camera. Yeah, it will be 1 minus the probability of A. Now, let us look at Venn diagrams. So when we are taking Venn diagrams, so Venn diagrams are a representation telling us, okay, this is a sample space. Sorry that I didn't put the borderlines. From where you can see my mouse moving, I hover around. Okay, as I hover around here, I hover around here and hover around here. So taking the first 2 cycles, one is being represented by A, the other is being represented by B. So the S is covering both A and B. So now these cycles are not overlapping with each other. So since they are not overlapping with each other, it means that there is no intersection. So in the language of probability, when there is no intersection, we say we say those events are mutually exclusive. So A is mutually exclusive from B since there is no intersection of them. So now when we look at the second diagram, so this is A, this is B. Now they are overlapping somewhere where there is a dark shaded area. So in this dark shaded area, this represent an intersection of the two circles. So these two, they are not mutually exclusive because they do have an intersection. When we say they have an intersection, it means that they have elements that are common in A and elements that are common in B. So these two events are not mutually exclusive. This one, they don't have common elements. We say they are mutually exclusive. I hope we are still together. Now, there are some things to note here. We sometimes shade in parts of a Venn diagram to illustrate a union, intersection, and complement. So you have to note of these things. So when we speak of a union, we mean that is or means union, then intersection means and, then complement means not. So the complement is not, the intersection is and the union is or. Now look at this, another example of this Venn diagram. If you look at 1, 2 in the first column, let us look at the 2 rows. These ones are mutually exclusive. So when you say they are mutually exclusive, this is the representation that we give them. Now, when you look at this one on the far right, so these ones are not mutually exclusive because they do have what? Common elements. So now here, there is nothing to shade here if they are mutually exclusive. So there's no intersection. So when you check these ones, they are not mutually exclusive. There is an intersection. When after the shading, we look at the dark gray area where we have those cross-sectional lines. So these ones are not mutually exclusive. That is how you have to draw your Venn diagram. So now there is that representation there at the bottom, A, union, B, all of that complement. How do you shade that? You shade that in this particular order in the sample space. Now, and also when they are not mutually exclusive, how do you shade that? You shade that as well in that particular order. The intersection is not to be shaded. Okay, I'm running fast. Okay, now let us look at this. Example 1. If A is the event that a person is arrested for drunken driving, and B is the event that a person is a male, describe in words the shaded region in each of the following diagrams. Now, we'll look at this one, and also we'll also look at this one. Say A is an event of a person being arrested for drunken driving, and B is the event that a person is a male. So this one, B, represents a male. So A, it represents that a person is arrested being drunken for driving. So a male who is arrested for drunken driving, that is how we are going to shade it. A female who is arrested for drunken driving, we are shading the other side. Now, a female who is not arrested for drunken driving, that is how we are going to shade that sample space. A male who is not arrested for drunken driving, remember here they are drinking and driving, here is none. So these males are not being arrested for drunken driving. A male or a person arrested for drunken driving, so it means that we can check it can either go both ways. That is how we are shading those particular Venn diagrams. Now, let's Look at this Venn diagram and let us look at the scenario. There are 222 boys in grade 11, just like you, at Sunnyvale High. 160 of them, 160 play rugby, 110 play cricket. All right. 70 play rugby and cricket. Illustrate this information in a Venn diagram. How are we going to illustrate the whole of this scenario? Okay, first of all, or first and foremost, this is 70 will represent A and B. 70, we are going to say it's A and B, rugby and cricket. Therefore, 110 is just cricket. This is B. 160 is rugby. Now, for you to get your calculations correctly, you must first plot your intersection. So you plot your intersection here, which is 70. So 70 will play rugby and cricket. Now, how are you going to find the remainings? They told you that 160 plays what? Rugby. So now you are going to say 160 minus 70. So what is 160 minus 70? This is 90. This 90 here, they play only rugby. So the 70, they play rugby and cricket. Now, those ones who play rugby in general, they are 160. When you add 90 plus 70, it's 160. So those ones, they play rugby in general. But those who play rugby only, they are 90. I'm not so sure whether that one does make sense. So now we come again, we look for those who play cricket, the overall of cricket. Remember, the 70 here, it does play cricket as well. So now when we want to find the overall who plays cricket, so we are going to say 110 minus that intersection, those who play both cricket and rugby. So you are getting 40. So now the total now, so when you add now 70 plus 40, so this one should give you a 110. So now you have illustrated the information that they've given you above. But remember, now let us add these numbers to see whether, what are we getting? So 90 plus 70, that is 160, plus 40, that is 200. Oh, we have 200, but they've told us there that 220 points. What happened to the other 20? So the other 20, they do not participate in any of the sports. So you have to write the 20 outside of these circles. So the 20, they do not participate in anything. They are just spectators. They don't play. They are just spectators. They don't participate in any of this. So these are we can call them the fans. Yeah. So we are sitting there in the grandstand. So these ones, they don't do anything. So this is your sample space all in all. So now find the probability that a boy chosen at random plays rugby or cricket. We are choosing whether the person will play either rugby or the person will either play what? Cricket. So that is the union of this thing. In reality, we are looking for a what? For a union. So when we look for a union, that is how we are going to find that. So we are going to say this plus that, all divided by the sample space. So when we divide by the sample space, that is going to be 10 over 11 when you have already simplified it, of which is 200 over 220. Simplify this one is 10 over 11. Now, the next question says, plays neither rugby nor cricket. So it doesn't play any of the sport. Now we are looking for a complement. That is where the complement comes in. So we are going to say, remember this formula that we have Now is the time to bring this formula. So now we are going to use this formula. So it doesn't participate in either rugby nor cricket. So now this is the formula that you want. We want those ones who do not participate in anything. So now so when you look at it, you can say 1 minus that thing, 1 minus this. So you are going to get 1/11. Or you can just say, oh, those ones who do not participate in anything. So that should be your 20/220, of which is 1/11. So place only one of the two spots. Now they are asking you, all right, place only one of the two spots. Now, okay, how do I get there that this person plays only one of the two spots? So now we look, there is this one, of which is he plays only rugby. He plays only cricket, of which what is 90 plus 40? Okay, 90 plus 40, it's 130. Okay, over 200. So now my probability will be 13/22. When you simplify this, divide by 10, the numerator and the denominator is 13/22. So he plays only one of the two spots. So we are looking for the probabilities where without the intersection. So it should be 90 plus 40 or divided by 220. Now they say does not play both sports. Okay, it doesn't play both sports. Now you check, the person doesn't play both sports. All right, it doesn't play both sports. You check, these two, they play both sports. The 70, they play both sports. So now it doesn't play both sports. There is this one for rugby only, and there is this one for cricket only. So now I've got my 90 and I've got my 40. These ones, they only play one sport. And you've got this 20 that does nothing at all. So it's going to be my 90 that plays rugby only, plus my 40 that plays cricket only, plus my 20 that does nothing at all. So does not play both sports. So that should be 150/220. So divide by 10. Okay, you can factor out 10, all of them. So now you have what? 15/22. So that is how you use a Venn diagram to analyze any situation. So this situation was analyzed using a Venn diagram, and you can easily pick up those probabilities from there. Remember that your 220 is your S, of which is the sample space. Now, they've given you now in another problem to solve in decimals. So since they have given you the problem to solve in decimals, you've got the probability that a grade 9 student chooses math as a subject is 0.7, that is 70%. And chooses geography is 0.3, okay, we can say maybe it's 3%. The probability that he takes neither of the two is 0.2, okay, maybe that's 30%. It doesn't take any of the two. All right. Now, remember, they didn't give us the percentage or the number. that it takes both subjects, what is going to happen? They didn't give us that one. So find the probability that it takes both math and geography, that it takes only one of the two subjects. Now, you've been given a hint here. Always put the intersection in first, then build. All right. Now let's look. They didn't give us that particular number. So since they didn't give us that particular number, it means that it is unknown. So let's look at for the unknown. We are going to call the unknown X. Okay, you can call it the variable that you want, but our variable that we like now is X. So X is our unknown that some of the student or the student will take both math and geography. So our intersection is X. So now what will be the probability that the student will choose mathematics only? So it should be 0.7 minus the intersection X, the unknown. What is the probability? Okay, we are looking. Now the student will take, what will be the probability that the student will take geography only? So it should be 0.3 minus X. So now they've already given us that the students will neither take any of the two. You won't take any of the two. So that one is being given as 0.2. So that 0.2, it doesn't participate in any of the choices. So we put that 0.2 outside here of these events. So this is the 0.2. Now, remember, the probability of the sample space, you must always add it to what? It must always give you what? 1. So since it must give you 1, so how are we going to find the intersection of which is 0.2? Now, let us look how we're going to find that intersection of which is 0.2. So we are going to add the probability that the student takes mathematics only plus the probability that the student takes both mathematics and geography, and as well that the student will take geography only and the students will not take either geography or mathematics. Then you have to equate that one to 1. So it should be 0.7 minus X plus X, which is this one, plus 0.3 minus X, of which is mathematics only, plus the 0.2, you equate it to 1. So now negative X plus X, that's a 0. So you'll be left with this minus X. So now you'll be left with 0.7 plus 0.3 plus 0.2. So if you add this one, 0.7, 0.3, that is a 1, plus 0.2, that's 1.2, minus X is equals to 1. Therefore, transpose X to the other side. Therefore, you will have 1.2 minus 1, of which will give you 0.2. So your X is 0.2. So X is 0.2 here. If X is 0.2 here, oh, already now I know. Okay, for mathematics only, that is 0.5. Then for geography only, that is 0.1. So what's the next question? The next question, he takes only one of the two subjects. He takes only one of the two subjects. So if he takes only one of the two subjects, so what is the probability of mathematics only? Remember, you put your 0.2 here. 0.7 minus 0.2, that's 0.5. Plus, remember, you put your 0.2 here. 0.3 minus 0.2, that is 0.1. So now 0.5 plus 0.1. These are the probability that it takes geography only, mathematics only. So those probabilities for only one subject only, it's 0.6. So that is how you approach this question by using a Venn diagram. So you must not be confused by these things. If you have a question, please write it in the chats. So we will address the question as we go along. So anyone who have a question, just write it in the chat. Let me just pause there for 30 seconds. If you have a question, just write it in the chat. So for these two problems that we have discussed so far. Tubazane and Snare, please tell me if there's a question that is coming through the chat from the students. Okay.
Oh yeah, there's no question so far.
Okay, since there's no question, okay, it means that let's proceed. Green lights. Okay, since it's green light, now let us look at this problem. Now we have been dealing with the two events. Now we have like three events now. Let us see what these three events hold for us. Now let us look at these three sets. A study into other subject taken by 239 students for mathematics at Sherlock High School in 2006 yielded the following data. They tell us that all about 12 wrote one or more of history, okay, geography, or science. Now, they are just telling us about these ones. So it's all but 12 wrote one or more of history, geography, or science. So now 120 wrote geography. Note that number down. 154 wrote science. Note that down. 51 wrote history and geography. Now, if you are going to solve this particular kind of a problem, you must first focus on the intersections. Now, if they have told you that 51 students wrote history and geography. So now we are going to have a set for geography, a set for history, and a set for science. 51 of them wrote history and geography. So the intersection of history and geography, it should give you 51. 67. They say 67 of them, 77 wrote geography and science. Now, that's another intersection that you should bear in mind. So they tell you that 77 wrote geography and science. Normally, with this kind of scenarios, they normally give you two intersections and they will never give you the third one. Now you have to see how you get the other one. So now they say 67 wrote science, but neither geography nor history. So bear in mind, this one 67 is for science only, Now, when you fill this up, okay, for science only, I've got 67. Oh, this is my 67. I put it here. That one is for science only. Then they say 40 wrote all the three. So now I come to my Venn diagram. I look at my Venn diagram. I must make them intersect, the three of them, because they have told me now that 40 wrote all three of them. It means that there's an intersection where 40 students wrote all those subjects. They took them all. So now the intersection, I'm looking at the intersection where all of them are meeting. That's 40 here. This for science is overlapping here, for history is overlapping here, for geography is overlapping here. I put 40. Okay, but for history and geography is 51. Oh, okay. Since I have 40, what's the other number that I can get to 51? Or I would say 51 minus 40, of which is 11. So these 11, they only took history and geography. There are 11 students that only took history and geography. There are only 11. Oh, all right. However, 77 wrote geography and science. Okay, let me look at the intersect of geography and science. This is geography and this is science, but 77 of them. However, 40 took 3. So I would say 77 minus 40. Then I get 37. So 37 students, they took geography and science only. Okay, all right. Now I do have the, now remember for geography, I have what? 120. So now how am I going to get to 120? So now for geography only, I have to calculate all these numbers. You see, I'll have to say 120 minus 11, minus 40, minus 37. So these numbers, when I subtract them from 120, the remainder that I'm going to have is 32. So this 32, now it will yield the 120. Now, what is the number of all those students that took history and science only? They have taken history and science only. So now, remember, they have already they've also, okay, they've already told you that 154 took what? Wrote science. Okay, 154 took science. 67, they have taken science only. Okay, so now let me focus on science. With science, I will have 154 minus 67 minus 37 minus 40. Oh, okay. What am I left with? I'm left with that 10. So when you add this now, you have what? You have your whole 154. Now for history, the number will just be a default that you are going to get. So remember, you have that 12 that didn't participate in anything. So you put the 12 here. They didn't participate in any of the subject, those ones. So this is your sample space now. It has been filled. Now, remember, now they are asking you a question. Find the probability that a student selected at random takes neither geography nor science. So now we are focusing on those students that will not take geography and that will not take science. So it means that for geography, that student doesn't take, even here at the intersections. For science, that student doesn't take it, even here at the intersections. What are you left with? We are left with 30 students that took history only. So you have these 30 students that took history only, and you have these 12 students, so 30 that took history only, and you have these students that have taken what? Nothing at all. So it should be 30 plus the 12 divided by 39. This 39 is the sample space. So you have your probability as 42 over 39. So now they are asking you, okay, the student, any two, they say to you, how many? Any two of the three. So if any two of the three, remember, you've got students that will take history and geography only. You've got students that will take history and science only. We are looking at those intersections: history and science only, history and geography only, science and geography only. So let us look at those ones where only of those three subjects are intersecting twice. So now you've got this 11 where it's only history and geography. That's the 11. You've got this 10 where only history intersect with science. So you've got this 37 where science intersect with geography. So it's 37. So any two of the three subjects. So you have to take 10 plus 11 plus 37. So all divide by what? The sample space, of which is 58 over 239. Now they say to you, at least one of the three subjects. So to simplify this one, they say at least one of the three subjects. We can just like add all of these ones. We are going to get this number. But if you don't want to add all of them, there's a shortcut. So what is the shortcut? We are going to say 1 minus the probability of those ones who didn't participate in anything. So if we subtract those ones who didn't participate in anything, we are actually getting the number of students who have taken like at least 3 of the subject, of which is 1 minus the probability of none, of which is 1 over 1 minus 12 over 239, which is 227 over 239. So if you add all of these numbers here in these sets, we are going to get 227 divided by 239. So if you don't want to take the longer routine because you might make mistakes, just say 1 minus the probability of none. These are the spectators, so they didn't take any of these subjects. So it should be 1 minus the probability of none, of which we are going back again to use what? The I'm fast. We are going back again to use what? This formula, of which is the probability of the complement is 1 minus the probability of A, or you can say probability of A is 1 minus the probability of the complement. So that's what they meant in this question. Okay, let me just pause for 30 seconds and ask for questions. Is anyone having questions? Tuwazana, please check if there's a question that is coming in.
No question yet.
Okay. Let's proceed. A doctor told the family anxious about the condition of their daughter that the odds that she would make full recovery were 2:1. Then the odds against her condition remain unchanged, which were 7:2. The odds against her condition became worse, of which were 8:1. All right. Then determine whether the doctor's probabilities were possible. You've got better, you've got worse, you've got unchanged. So now, when when we represent this thing as probabilities, so here 8:1. So you want this thing in terms of a probability. So it means that the sample is 9. So 9 minus 1, you've got 8. Okay, so out of 9 chances, okay, only 1. So okay, the remaining is 8. That is worse. So you've got 1/9. So for this one, for full recovery, you would have like 2 to 3. For unchanged, remaining unchanged, so this one, it should be, the total is 9, therefore it should be 2/9. So it's 2/9. So these are the kinds of probabilities that you are looking at. So now the probability for beta should be 3/2. So these are ratios. So the probability for worse is 1/9. So the probability of unchanged is 2/9. So now you check, is the is the doctor correct? So now let's check whether the probabilities are possible. So let's check. So we have to add all of this. How are we going to add all of this? It's 3/2 plus 1/9 plus 2/9. So this one, we are changing it. We are going to look at the lowest common denominator. It should be the same. So we multiply by 3, we multiply by 3, we are going to get 9. So it's 6/9. So 6/9 plus 1/9 plus 2/9. So add all of these, 6 plus 1 plus 3, that's a 9. 9. So the doctor is correct. Okay, that was quick. These are the activities that you should look afterwards. So based on event diagrams. So you have to reverse or revert back to the event diagrams and the examples that we have looked. So for now, I'm not going to do these activities. You will do these activities on your own. Tubazane and Sneh, please include these notes when all the sessions are done so that the students will take these activities on their own. For the interest of time, we will not do them.
Okay, we'll do. Please make sure that you send them to Simo so that we can share them.
Oh, okay. I will send them to Dr. Simo so that he will send them. Yes, Tubazan.
Oh, okay. I was saying that maybe we can take a 5-minute break, then we can continue it for grade 12. Or just
Okay.
take a 5-minute break. But
There's a question on the chat.
Okay, please read the question to me.
How did you convert the ratio to a fraction?
Oh, okay. All right. Let's go back. Now let us look at this one. For this one, they say the odds against a condition remain unchanged. You've got 7:2. So now how do we convert this ratio into a fraction? So this would be 7 plus 2, you get a what? A 9. But now there is that number of which is this one, the 2. They say 7:2. This one must not change. So it should be 2/9. The 9 represent that the total of this thing. Therefore, this one, it should be remain your denominator. We cannot say over 7. So we just add this one. So that's the simplest conversion that I can do. Or also this one, 8 plus 1, that's 9. So you should have like 1/9. So why 9? So now you are splitting the 2. You take the 1 is worse than how many that are left after removing from the 9 is 8. So that is why the ratio is written like that.
No, all right. I think also Nokwanda was asking that question that you
Oh,
just asked.
okay. No worries. Okay, let's take the 5-minute break and wait for the others. Let me get some water in the meantime.
All right. Thank you very much. And grade 12, please don't forget that at 12 we have lucky draws. So please join that. It is for everyone. So if you want to do something, then you can just come back at 12. And then we'll allow Mr. Nkos just to rest for 5 minutes while we wait for grade 12 to log
To join.
online. Yes.
Okay. Thank you very much. Let me get water.
All right. Thank you.
Thank you. '11, we said you are going to continue doing these exercises. We will send the slides to you. So these are the questions that you have to go through them. Now, let us look at this one. So we're looking at data handling and probability. So what we will be looking at here is correctly identify dependent and independent events by using tables of diagrams. Use tree diagrams and Venn diagrams to solve problems where events are not necessarily independent. So these are the things that you should bear in mind or to keep. Now, recognize events that are independent or dependent of each other. So decide when to draw a tree diagram to find the probability. Use the intersection of which is the probability of A intersection B is equals to when you want that probability when events are independent. So this is the formula that you're going to use, where probability of A multiplied by the probability of B. Decide when to use a Venn diagram and when to use a tree diagram. So you must be cognizant of this stuff. Now let us look at independent events. So when you explain independent events, you will always get the definition of the other. Events A and B are independent if the probability of A is not affected by the occurrence of B. Events A and B are independent of each other if the probability of A is not affected by the occurrence of B. So you should note this. So I'm independent of my own. Snendlandla or Tubazale, they are also independent. So they should not be affected by whatever I do. So that is why we say those events are independent of each other. Examples are a coin tossed twice, a coin tossed, and then a die is thrown. So these are independent events. You guess two multiple choice answers. A boy is born, then a girl. Those events are still independent. You draw a card from a deck of 52. You replace it and draw another one. Those events are independent. But dependent events, choose two cards from a pack of 52. Choose two names out of a hat. So this one, probability of A and B is the same like saying probability of A intersection B, of which is the same like probability of A multiplied by the probability of B. So these are dependent events. You know that when it's dependent events, this is how you should get your intersection. Then in statistics, or means add. You must know that when they say or, it means that you must add, and means multiply. Be mindful of this language here. Note it. Now let us look at this example. If a coin is tossed and a dice is thrown, what is the probability of getting a head and a 6? One, you must get a head, the other, you must get a what? A 6. You look, how many outcomes are you going to have if you are tossing a coin? So if you're tossing a coin, you're going to only have two outcomes, which is the head and the tail. So it should be head and tail. That is your sample space. So when you are throwing a dice, so if you are throwing it, what is your sample space? You'll have your sample space as 1, 2, 3, 4, 5, 6. So those are the numbers that you must have in your sample space. So now the question is, what is the probability of getting a head and a 6? In your sample space of tossing that die, what is the probability of you getting a head? It should be 1/2 because you have got two outcomes. One is a head, one is a tail. So you should have what? 1/2. This is the probability that you are going to have. Then of getting a 6, you look at the sample space, you've got 1, 2, 3, 4, 5, 6. So since you've got 1, 2, 3, 4, 5, 6, how many times does 6 appear in that sample space? It appears only once. So it's 1/6. So now these are your probabilities. Now you must calculate the probability of getting a head and the tail. So now they want the intersection of a head and a tail. So those events, they depend on each other. So remember, when you have to choose out of the two, so now we have to multiply. So now you multiply the probability of a head and multiply by the probability of a 6, of which is 1 times 1 is 1, 2 times 6 is a 12, so it's 1/12. So be mindful of that. First, you must understand the sample space of what? Of a coin that is being tossed once. And you must understand the sample space of a die that is being thrown once. So these are the things that you should be mindful of them. I'm not so sure whether it makes sense. Now, let's look at a tree diagram. Tree diagrams are useful. Here they say to us, a box contains 3 coins. 1 coin is fair. 1 coin has a head on both sides. Okay. one coin is weighted so that the probability of its weight is 1/3. Oh, all right. If a coin is selected and tossed, find the probability that it is a head. you look at this. Find the probability that it is selected and it's a head. First, you have to draw a tree diagram. Your first 3 branches will be the branches of the coins. How many coins do you have in the box? You have 3. So it's 1, 2, 3. So all these 3 coins, they should share 1/3, 1/3, 1/3. So it's 1/3 for this one to appear in the box. It's also 1/3 for this one to appear in the box. It's also 1/3 for this one to appear in the box. Those are your first in line probabilities. Now, in the first branch, they've already given you that one coin is fair. If it is fair, it means that it has one head and one tail. So now this is the probability of the coin now. So one head and one tail. So remember the outcomes of the coin is head and tail. So how many times the head will appear there is once. How many times the head will appear there, the tail will appear is once. So it's 1/2, 1/2. Now we come to the second arm. One coin has 2 heads on both sides. One coin has 2 heads on both sides. It means that there is no tail. There is no tail in that particular coin. Since there is no tail in that particular coin, you look, oh, the probability of a head to appear on one end is 1/2. So it means that it has 2, 1/2 plus 1/2 is 1. So that is why we have what? 1. So tail 0. So that is how you got these 2 numbers. Now, they tell you again, one coin is weighed so that the probability of its head is 1/3. The probability of its head is what? Heads is 1/3. So they weigh the coin, they find that the probability of its heads is 1/3. Oh, all right. Under the branch of the head, so the weight there is 1/3. What should be the remainder? Remember, I should always, when I add the probabilities of the branches, I should get 1. So it means that the weight of the tail is what? Is 2/3. So this is how you draw up your tree diagram. Now, if a coin is selected and tossed, find the probability that it is a head. Now, how are we going to determine that it is a head? So if we are looking, they've already told us a hint that it should be what? A head. So in my branches, I have to go along the branches of heads. I'm not diverting to tails. I go along heads. I look, okay, here is the head. So with the first branch, then second branch, I focus on the head. I'm not coming here. I put this one as an X. I put this one as an X. I put this one as an X. I cannot come via tails. So for me to reach a head, I've got what? 1/3 multiplied by 1/2. That's the first head. The second head, the tail, the root to the second head, okay, it's 1/3. Oh, here, okay, a head here is 1. So it's 1/3 multiplied by 1. Here again, oh, I'm looking for the root of a head. It's 1/3, therefore multiplied by another 1/3. So the probability for you to get a head, you multiply all those probabilities. 1/3, remember they are dependent of each other. 1/3 multiplied by that 1/3 multiplied by that, 1/3 multiplied by that. So I've got 160, 1/3, 1/9. So you add all these numbers. The lowest common denominator here is 18. Therefore, you add all of these numbers. We are going to get what? 11/18. Do you have any question? Let me pause a bit here and see if they have a question.
So far, no question.
Okay.
I don't see it in the chat box.
All right. Since there's no question, let us proceed. Okay. Now, again, let us look at these three diagrams. So you guys, you must not be confused by three diagrams. Read your statements through. Read your statement through. Read your statement through. So a bag contains 5 red beads. That one, now they've already told you 5 red beads. You mark that one down. And 3 blue beads. Oh, there's another second class or type of beads, of which are blue in color. Oh, okay. Now, they are also telling you a second bag contains 6 blue beads and 4 red beads. Okay. In reality here, let me read the second line. If a bead is selected from one of the bags, find the probability that the bead is blue. Okay, in reality here, how many bags do I have? I have 2 bags. So each of those bags, it contains what? It contains beads. What is the color of the beads? I've got 2 outcomes or 2 options of colors, of which is, or choices of colors, is red and is blue. Oh, okay. I have 2 bags. Okay, 2 bags. My first branch should be 1/2, 1/2. Those are my first 2 branches because I've got what? 2 bags. So 1/2, 1/2. Okay. The weight of this one is 1/2, therefore 1/2. That's the probability because what? I have 2 bags. So 1 bag, 1 bag. All right. This is one of the 2. This is one of 2. Okay. Again, bag 1, it has beads. Bag 1, how many beads are there? In one bag, 5 red and 3 blue. So in total, I have 8 beads. 8 beads. Out of 8 beads, 5 are red. Okay, I've got my 2 outcomes, red and blue. 5 of them are red, 5/8. 3 of them are blue, 3/8. Now, in the second bag, I've got how many beads there? 6 plus 4, that's 10. How many are red? 4 are red. 4 of 10, they are red. How many are blue? Are 6. 6 of 10. Oh, okay. I've got this one. So here are my bags now. This is the tree diagram. I've represented my tree diagram very well now. So now I have to answer the question. So to answer the question, they say, find the probability that the bead is blue. Remember, we are going to travel along the route of the blue at the end of our tree diagram. So the end of our tree diagram here, this is blue. So we have to travel along the routine of blue. So I've got 1/2, that's a half. Then if we come here, which is 3/8. So it's half multiplied by 3/8. And also in the second leg, we have to travel along the outcome of blue. So it's half So do we go decide? No, 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 no. This one is red. We are not going there. It's a cross. We go here. Blue. Okay. It's 6 over 10, of which is the same as 3 over 5 if you simplify it. So I have 1 over 2 times 3 over 8 plus 1 over 2 times 3 over 5. So you multiply this is what you get. Any questions so far? Okay, means no question. Let's jump to the next slide. Here we go. Go again. Okay. A bag contains 2 red balls, okay, 3 yellow balls, and 4 white balls. If 2 balls are selected, one after the other, find the probability that they are both the same color, no red ball is selected. Okay, first and foremost, here you've got only one bag, but they gave you the choices of colors. What are the choices of colors? They say is red, yellow, and white. Oh, okay. Red, yellow, and white. All right. How many are, let's add the balls. 2 plus 3, that's 5. Plus 4, that's 9. So I've got 2 of 9. I've got 3 of 9. I've got 4 of 9. These are my arms or legs. Now, listen properly or read the second statement properly. If 2 balls are selected, one after the other, find the probability. One after the other. Now, you've got 2 of 9. Okay, here you've got a red. Okay, the outcomes here at the end, you should have what? After selection, a red, a yellow, and a white. All right, we are selecting them one after the other. If we select a red, we remove a red, we are going to be left with what? 1 over 8. But now we have only selected a red, we cannot select a yellow, so you should be left with 3 over 8. Here, you should be left with 4 over 8 is the white. We have already taken out that one red. We come here, we follow the route of the yellow one. Now, we select again. Since here it's yellow, there's no possibility for us to take out a red from the yellow. So the red remains 2. Since we have already taken out a yellow, this one, it will remain at 8. So from 9, take 1, it's 8. So now a yellow, yes, we can take a yellow. So we remove that one, it should remain a 2. Then from 3, take 1. So we remove that one. So it's 2 of 8 here, it's 4 of 8. This one is not being disturbed. So with the white, we follow the same routine, one after the other. So the red remains as the same. The total here, it changes from 9 to 8. The yellow will remain as 3 of 8, but the white now changes from 4 to 3. So these are the outcomes. So now you come that both are the same color. That both are what? Are the same color, that both balls are the same color. So if both balls are the same color, you should have, like, if we check here, the color should be red, 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 yellow, red, white. The outcome here, RR, RY, RW. We come here, we check YR, YY, then YW. Come here, we check the outcome is WR, is WY, is WW. So we are focusing on RR, yellow, yellow, YY, WW. So those are the outcomes we are focusing on. So now, red, red, or yellow and yellow, or white and white. Red, red, it should be 9 by 2 multiplied by 1 of 8. The first one. The second one, yellow and yellow, 3 by 9 multiplied by 2 by 8. The third one, 4 by 9 multiplied by 3 by 8. This is it. So add your multiply, that one is 2 over 72. 6 over 72, excuse me, 12 over 72. You add all of that thing and simplify, you got 5 over 18. Now they say no red ball is selected. No red ball is selected. It means that we don't want red. Red must not be what? Selected. Any option that has a red, it must be taken out of the equation. Red, red is out. Red, Y, yellow is out. Red, white is out. So in the first arm, we are not going there. Now let's check the second arm. Yellow, red is out. Yellow and yellow, we take that. Yellow and white, we take that. So that's 2, yellow and white. Yellow and yellow, yellow and white. Good. Let's check the third arm. White and red, no, we don't want that one. White and yellow, yes, we do. White and white, yes, we do. So those are your probabilities that you are going to be checking on. Yellow and yellow, yellow and white, white and yellow, or white and white. So now let's multiply all those probabilities. Like yellow and yellow, 3 by 9, 8 by 2. First option. Second one, it's 3 by 9, 4 by 8. Second option. Third option should be 4 by 9, 3 by 8. Fourth option should be 4 by 9, 3 by 8. That's one. So you add all of this after multiplication. So you've got 6 over 72, 12 over 72, 12 over 72, 12 over 72. You add all of that and you simplify it. Therefore, you get 7 over 12. That is to answer your second question of a tree diagram. The probability of South Africa winning the Pro 20 cricket match when Smith analyzes the game is 0.9. Okay. The probability of them winning the game when it does not analyze the game is 0.5. The probability of Smith analyzing the game is 0.2. What is the probability of South Africa that he will win? Or South Africa wins. Now let's check. We've got now, he analyzes the probability of South Africa winning the Pro 20 cricket match when Smith analyzes is 0.9. The probability of winning the game when it does not analyze the game is 0.5. The probability of Smith analyzing the game is 0.2. What is the probability that South Africa wins? Number one, we started analyzing. We will analyze whether it will win or lose, but we'll start by analyzing and not analyzing. So those are the two arms. You've got the arm of analyzing and the arm of not analyzing. The probability of Smith analyzing the game is 0.02. You analyze the game, you give the arm 0.02. It doesn't analyze the game, you give the arm. Remember, does not, it comes from analyzing. So you just say 1 minus this 0.02. Remember that formula at the back top of our slide of saying like you want to find the complement, it should be probability of the complement minus 1 minus the probability. Yes, so this is the 1. So 1 minus 0.02, it's 0.98. So here it does not, here it does. Now, remember, when he analyzes the game, we go back. The probability of South Africa winning the Pro 20 cricket when Smith analyzes the game is 0.9. So we go along analyzing the game. So we analyze the game, we find that it is 0.9 of winning. So what is left? So it means that 0.1 will go for losing. We also go again when it does not analyze. You see, when it does not analyze, yes, the probability of winning the game is 0.15. So of winning is 0.15. Of losing when it doesn't analyze is 0.85. You are going to say, how are you going to get the 0.85? It's 1 minus 0.15. So you're going to get this one. This is how you do. Now, what is the probability of winning? So now we take along the wins. So where your outcome is win, where your outcome is win. So is 0.02 times 0.09 plus 0.98 multiplied by 0.15. So that's the probability of winning. This is your probability of which is not 0.165. So the tree tells a story. You need you need a number on each branch. So that's how you you plot a tree diagram being given numbers. So be mindful of that. Any question? Seems like how much time? How much time do we have to buzz that?
I think you have 10 minutes.
10 minutes.
Yes.
Okay, let's see, where are we going? Okay, let's look at this activity. Venn diagram or tree diagram? Let's look. What are they saying? What are these people saying? In a large group of people, it is known that 10% have a hot breakfast. All right. 20% have a hot chocolate. Sorry, hot lunch, I mean. Hot lunch, and 25% have a hot breakfast and a hot lunch. Okay. Find the probability that a person chosen at random has a hot breakfast and a hot lunch. Now here you have what? both the probabilities, find the probability that, okay, a person chosen at random has a hot breakfast and a hot lunch. You have to choose now whether a tree diagram or a Venn diagram. So those are our choices that we have to look at. But by looking at the statement, the intersections have already told us that we are going to have a what? We are going to use a what? A Venn diagram. So remember, with tree diagrams, we don't have what? We don't use those words of and what are the intersections. So these ones, since they've already told us in the statement, so it already tells us that this one, it is an intersection. Now we've got our sample space there. 10%, okay, in a large group, it is known that 10% have a hot breakfast. 10% they have hot breakfast. 20% have hot lunch. We've got those ones who have hot lunch. Then have hot lunch. And okay, 20% have hot lunch. 25% have what? Have a hot breakfast and a hot lunch. Now they are telling you that 25% have both hot lunch and hot breakfast. Find the probability that the person chosen at random has a hot breakfast and has a hot lunch. So now you need to put the intersection at first. So how do you do that? You have your point 1, of which is your hot breakfast. Therefore, now you've got that 25% that have what? Both hot and what? A hot lunch and hot breakfast. Therefore, you've also got that 20%. So when you do your calculation, you've got your 0.1 and your 0.2 minus your x, of which you don't know, you are looking for, which is the probability of a person chosen at random. He has a hot breakfast and he has a hot lunch. So all of those ones, you are going to equate it to that number, which is 0.25, 25% who have both hot breakfast and hot lunch. So of which you've got your 0.3 minus 0.25, which is 0.005. This was quite a simple one. Let's look for this one. A teacher discovered that 75% of his students do their homework regularly. That's the struggle. We know that most students, they don't give a damn about doing homework, but I hope you are not the ones who are not who are always doing their homework. He calculated that if a student regularly did their homework, the probability of passing their exam is 0.8, of which is 80%. And if the student does not do their homework, the probability of passing is only 4%. Okay, 0.4. Okay, sorry, 40, not 4%, 0.4. Calculate the probability that a random selected student passes the exam. Okay, number 1, the first branch or leg, it should be you do your homework or you don't. That is why we have done and not done. So of doing, it's 0.75. So of not doing, it's 1 minus 0.75, which is 0.25. Now we come to the passing part. If you are doing your homework, you have 0.8% or chances of passing. So the chances of failure, which should be 1 minus 0.8, which is 0.2. Here, the chances of passing, they've already told you it's 0.4. So it's 0.4. So it's 1 minus 0.4, which is 0.6. Now, calculate the probability that the student will pass. So now we are going to look at both legs from the beginning, but our end outcome should be pass. So we do away with failure. So we do away with F, we do away with F. So now it should be 0.75 minus times 0.75 times 0.8, 0.25 times 0.4. So these are the numbers, of which is 0.7. Here are the activities that you will have to do, because for the interest of time, we won't do them now. You will do them on your own when we send the slides. Yeah. That's all, folks. Thank you very much for your time. Thank you, Mr. Tubaza.
Thank you very much, Mr. Nkosi. That was a lovely presentation.
Thank
I
you,
enjoyed
sir.
it.
Thank you. You're welcome. Nice to hear that a mathematician has enjoyed the session.
Yes, I did. So those who have questions, you can send us a question, and then we'll let Mr. Nkosi know or what types of problems that you want us to solve next time.
Yes.
Yes, but at 12 we have a science show and lucky cross. Please join that one.
Okay,
So-
I will join it, sir. For now, let me quickly rush to check some of the mails that have been coming through. So yeah.
all right, thank you very much. Thank you.
Okay,
Thank
very
you,
much.
Mr.
Cheers.
Nkosi.
Thank you very much, Sneh. You are welcome. I will see you at 12.
Afternoon, Dr. T. Dr. T, we ready for you. You can start anytime.
Okay, let me just switch on my camera, and I'm here in the half dark. I thought we're going to do something appropriate, to load shedding and so on. So today what we're going to do is we're going to do a little bit of what I call science magic. And I brought some experiments with me, and we had a guest here who was fantastic in doing science magic. And I'm going to show you my very first experiment. Okay, so what we've got here is some table salt, and we're going to put it on here. Okay, so let me just get a little bit out here. All right, a little bit. Here we go, as everybody can see. And if we can just make the screen large, Tembalani. Sorry, with me, I've also got like Tembalani, and I've got some Kayla. And I hope that everybody can see me, that you can see the salt here in my hand. All right, here we go. And now we're going to make the big disappearing. Okay, everybody's watching. Everybody's watching. Okay, it's here. It's here. And now we're going to make it disappear. As you can see, it's gone. Fantastic. Science magic. But you know, of course, that this is not magic, that this is science. We just dissolved the salt in the water. Okay. So as you can see, we dissolved it. It will take a while to make it reappear. Okay. So probably like 2 weeks. Then, of course, the water will evaporate, and what you see as a residue is your salt. So it didn't really disappear. It just basically dissolved in the water, and so that we can't really see it. So what I've got here is a mug. And what I can do now is I can make a Mercedes appear just with this mug here and a little bit of hot water. Now, this is what I call science magic. So let's see. So I've poured some water here. I've got my mug here, and I hope, because I'm working in the semi-dark, I hope it's going to work out. I'm going to fill my cup with hot water. I'm going to fill it up. And I should have put on my glasses, you know, at some age. Yeah, a little bit more. No, I think it's fine. It's fine. It's fine. Okay. So let's see. And let's see how the magic works. Oh, is it only half full? Okay, so maybe half a Mercedes. Okay, so we're gonna add a little bit more. Cool. Yeah. Here we go. So as you can hear in the background, I'm not alone. I've got my trusted assistants with me. I've got some Kayla with me and Tembelani. So Tembelani is the one who's shaking the camera. And some Kayla has got the very important task of, you know, switching on and off the lights. So, and here it is. There is our Mercedes. Here we go. So, how does it work? As you can imagine, it's not magic. This is simply a glaze that basically changes from black to colorless, which is called a thermochromic glaze. Okay, so thermochromic basically means that you have a molecule that changes with temperature. So it appears black when the water, or when the surface is cold, and colorless when the surface is hot. So if I'm going to put my hand on it and it's really, really hot, or put ice cubes on it, it will turn back into black. And we can see this probably at a later stage. Okay. So as you can see, we've got lots of exciting things. So we can change color. We can make things disappear, appear, just by using temperature. But let's see how it works out with light. So what I've got here is, as you can see, we've got some beads here. We call them ultraviolet light beads. Okay, nothing special. And as you can see, the color here is, maybe some of you up there, you know, on the other end here, that's sitting there, can tell me what the color is. You can unmute yourself and shout it out. What is the color here? I can see probability. The probability of somebody unmuting themselves is very, very low. Okay. Okay. So as you can see, it's colorless, right? And let's see what is going to happen if we shine an ultraviolet light on it. So this is an ultraviolet light here. Timberline, if you can just move up so that you can show the flashlight here. This is used to hunt scorpions and so on. And what I'm going to do now is I'm going to shine my ultraviolet light on the beads. And I hope that you can see that they in fact changed color. There we go. Right. So what we've just learned is we can change the color using temperature, but we can also change color using ultraviolet light. And this is not called thermochromic. Thermo means temperature. This is called photochromic. So basically changing color with ultraviolet light. So what kind of application does it have? Apart from that, it's very cool, you know, to have these UV beads. So you can check out, for example, when you go out into the sunlight, if it changes color, and if you need sunscreen on, so you can test your sunscreen. Also, you know, of course, if your sunscreen is working, also if your sunglasses actually basically absorb the very dangerous ultraviolet light. So you can try this one out as well. You can also use the effect, for example, with glasses. I don't know if you've ever seen some of the glasses where people go inside and, you know, suddenly, and they go out, so inside they are normal glasses, and when they go outside, they are turning into dark glasses, all right? So this is the same effect, photochromic effect. The molecules basically change their shapes when the ultraviolet light comes onto it or shines onto it, and it's a reverse, what we call a reversible process. So as soon as the light goes away, fades away, the molecule changes back into its original form, and as you can see, the result here, the beads are colorless again. All right. Okay, moving on to things that you can do in the light during nighttime. I thought I'm going to bring you some load shedding experiments. And what we've got here is something that you all know. Ta-da! Glow sticks, isn't it? You all know the glow sticks, right? And what do? They glow in the dark, isn't it? So perfect, great for load shedding. So, and just to demonstrate how perfect they are for load shedding, if we can have the light switch off now. And as you can see, not much happened. Can we have the lights on, please, again? Okay, right. So nothing happened. Why not? Okay, so first of all, we have to understand how these glow sticks start working and what we find inside the glow stick, right? What I've got here again is my ultraviolet light. And if we now can switch off the lights, please, and I shine the lights on it, you can see that they kind of start glowing here. I hope that everybody can see this, but only when I shine my ultraviolet light on it, okay? So what we have inside here is called a fluorescent dye. And we're going to come back to the fluorescence just now. Can we have the lights on again, please? Okay, so you also find fluorescent dye, for example, in your highlighters, okay? You find fluorescent dye even on a 50 Rand note or 100 Rand note. So this is what people check for when they, you know, when you're at the cashier and you just chuck it in and so on. So they're basically checking for the ultraviolet light marking. Unfortunately, I wanted to show it to you, but unfortunately, it didn't come out quite nicely on the screen. So if you want to see it, you have to come bring your money to the science center. We love to take your money, okay? And then we can go into the dark room and we can put it underneath the fluorescent light, if you UV light, if you don't have one, and then we can check if it's really glowing and so on. All right. What I've got here now is a nice picture. And I hope that everybody can see this. Yeah, I'm quite the artist, as you can see, right? Here we go. So quite the artist. And if we can have the lights off, you can see nothing. But if I'm going to shine my ultraviolet light on it, you can see how nicely some of the colors actually start to glow. So because I'm using ultraviolet ink, fluorescent ink, okay? So fluorescent ink. Right, and if Thembelani stretches out, he puts the camera into the other hand and stretches out his arm, as you can see, nothing, you know, right? But if we're going to shine the ultraviolet light on, hopefully you can see how nicely his tattoo is actually glowing. So this is when you're really keen on having a tattoo. Can we have the lights back on, please? Because Thembelani is going to show you his arm in natural daylight. You can really not see much. Can anybody see the tattoo? Not probably. Only if I shine the ultraviolet light on it. Okay. So again, I use the highlighter to make this tattoo. All right. And so if you are dark skinned colored and you want to have a cool tattoo and go clubbing, which you shouldn't do at your age, okay? So there you basically just have to draw your tattoo on your arm using a highlighter, right? And then when you go into the ultraviolet light, it starts glowing. So you can try this out. Okay, coming back to our little glow sticks here. So remember, when we switched them on, or when we switched off the lights, they didn't do anything, all right? So no glowing, no nothing, and so on. Only when we put, oops, sorry, only when we switched on our ultraviolet light. Here we go, they started glowing. So what actually do I need to do? What do I need to do? I want to make them glow. I want, you know, to have light when it's dark. So Caleb, do you have any suggestions?
Maybe.
Tamalani just did this. I don't know if somebody can translate it for me, you know, whatever that is. So Caleb, do you know what this is?
Sounds like, looks like breaking.
Oh, breaking.
Yes.
Okay, you want me to break this?
Yes.
Eesh. Okay, all right. So let's try and break this. Right, so let's see. Ooh, I can already start seeing things. Can we just have the lights off, please? And you can see, already start seeing that they really start glowing in the dark. Let's see the other one. Hey, here we go. Let's just check it up a bit. Just checking up a bit. You know, I like to check things up. Here we go. Oh, wow, look at this. Okay, so fantastic glow sticks, but why did they actually start glowing? So remember, we had our fluorescent dye, and I don't know if you've heard it, if my sound was okay, because inside the glow stick, there was something else. There is usually like a glass piece, and inside there's another liquid called hydrogen peroxide. So we have our fluorescent dye with some other chemicals, plus a hydrogen peroxide, and this is basically what makes your glow stick glow. So you need to activate the glow stick. So you have your hydrogen peroxide plus the dye that is inside, and they produce another chemical plus light. Right. So let's see. I mean, it's a bit dim, hey? Let's see if we can get it a little bit brighter. So what I've got here, I've got some hot water here. All right. Luckily, I've still got some hot water. Right. Let's see what is going to happen if we dunk these ones into the hot water. Okay. Please, if you try this at home, do not use boiling water because it will melt your plastic and it will cause a huge kind of mess. So please do not do this. Right, and if I'm going to take them out, so remember the bottom part is dunked into the hot water, you can actually see a change. Can everybody, I hope everybody can see. You can change this, the bottom part is in fact shines brighter than the top part. Does everybody see this? Yes, no, maybe. Okay, cool. Right. So if we put it in, it shines brighter. And this is just due to the hot water. So what is basically happening is that we are increasing the speed of the chemical reaction. Can we have the lights back on, please? So we're increasing the speed of the chemical reaction. So we have our chemical A and our chemical B reacting very, very, very fast. Okay, reacting very, very fast. And this is why it produces lots of light. So if I'm going to put it back into cold, coolish water, and unfortunately I don't have really cold water, so I usually put in ice cubes. You can try this out as well. But you can already see that it's getting dimmer. So you can basically determine the brightness of your glow stick using different temperatures. The problem, of course, is with the glow sticks, they don't glow forever. I don't know if you've ever realized it. So if you want to have your glow stick glowing for a very, very long time, what you can do is you can kind of put it in the freezer. It's got the disadvantage that you really don't see them glowing in the freezer. Or if you want to have like a cool, bright light, you just put them in hot water unfortunately, then your glow stick doesn't last that long. So just to show you again, right, that it's not some magic trick or whatever, just some hot water. I'm going to put the glow stick in again. Right. And you can already see that it's getting brighter. Right. Thank you. Okay, so now moving on, and I don't know how many times. Okay. So moving on from my glow sticks to something else. So what I've got here, this is, and if you've been there on Wednesday, you might have seen this. This is a blue laser. I'm just pointing onto it. So a very high energy laser. And we're going to come back to this one here just now. So there's another effect that we are going to see. And this effect is called phosphorescence. So we have fluorescence. And sorry, I should mention that you find fluorescence again in your highlighter, in your glow sticks, on your banknotes. And if I'm going to do this, can you just switch off the lights again?
Aisha, hopefully you can see that you have them in your teeth as well.
Okay, they start glowing because you have a mineral in there that resembles apatite, the mineral apatite. And this is also what minerals do. Some of the minerals also fluoresce. Unfortunately, I didn't bring a sample, but again, if you're going to come to the Science Center here, we've got a fluorescent cabinet and you can watch, you know, how ruby glows, very nice red under ultraviolet light, and some other nice minerals. Okay, right, coming back to our phosphorescence. Okay, so what I've got here is a simple piece of canvas. And maybe what I just need is to have the lights off, please. And as you can see, you can't see really much on it. Okay, and if I can have some careless hand, can you just put your hands on the canvas? And now we're going to do some spooky stuff. Because what I'm going to do is I'm just going to move my ultraviolet light around the canvas. Okay, and I'm going to steal now some careless hand because I need it for future purposes, so I can always revert back to him when I need a helping hand. All right, here we go. And if you're going to take it away, there is your helping hand. So you can easily reproduce your helping hand here. Also, with a laser, what you can do is, this is a high energetic laser, right? So with a laser, you can also start nicely doing some cool art on it. Okay. So this is glow in the dark, something that you know from experience. And if Samkela can just run back and get something else. Okay, we can show you where the application is. All right. So here you can see where it's been covered by Samkela's hand. It's not glowing, only where it's exposed to the ultraviolet light. And here we have another joke that you've probably found on Halloween. If you can just move around. And I think we have to spice him up a bit. Okay, let me just make him glow a little bit more. Here we go. And suddenly we have our very perfect glow in the dark. Hopefully you can see glow in the dark Halloween skeleton. So again, if you want to see a skeleton and the cupboards here, you just have to come to the Science Center. Right, can we have the lights on, please? You know, these guys are always up for no good. They're always up for nonsense. All right. So how does it work? Okay. So with the fluorescence and the phosphorescence, so let's go start with the fluorescence. What you have is you have electrons on the outer shell, all right? So when I shine my high energy light on it, because this is what ultraviolet light is, it's a light with very high energy. What happens is, and maybe you can just turn around and follow me. Follow me, follow me. Right, so I'm now an electron, okay? I'm an electron, all right? So, and now I'm very excited because now the light, here we go. The light shines on me, the ultraviolet light shines on me, okay? Right, I'm getting very excited. So I'm basically now going up to a higher energy level. Right? So now, because I'm all excited, I'm up at a higher energy level, and now I don't really, want to be there because it's a bit uncomfortable. It's too high, and if we can have the lights off. So now I'm reverting back to the, and I hope that I don't fall. I'm reverting back, and now I'm emitting light in the range of the visible light. Right. So this is basically the principle of how fluorescence work. Right. With phosphorescence, you know, the electrons are a little bit more comfortable at higher energy level, and they're giving up the light a little bit. This is a little bit slower, a slower process. And that is basically it from my side. And I'm too early, but that doesn't really matter because I had enough of talking today. So I hope you enjoyed our little excursion into the world of strange materials, science magic. And I hope that you try out some of these, experiments. And see you next time. Bye-bye.
Thank you, Dr. T. Maybe can you take a few questions so that we can have winners, maybe 3 questions about your show?
Are there any questions? You know, you've done probability beforehand, and I would say the probability of these guys asking questions is like, okay, we'll see.
Did we lose Dr. T? Yes, Yabonga. What happened to Dr. T? I just lost connection for a second.
Hi, Snake.
Hi, Simo.
Yeah, are you guys done?
I think I think I and Dr. T lost connection during the same time and she's not back, but she was done with her show. We're just going to take a few questions from her to have our winners.
Okay.
And I don't think she's back online, so we're gonna do it randomly. Like
Okay.
Wednesday, yeah.
Oh, like that other day.
Yes.
Mhm.
I'm just extracting the spreadsheets for me to stay. Okay, I'm with Dr. T, and she will ask questions so that we can have our winners today.
Okay. Sorry, guys. I'm just disappearing. I'm appearing here. I've lost connectivity. And I disappear as well, you know. This is what I call science magic, you know. I'll you know, the appearing and disappearing act and so on. Who can tell me? Okay, thank you. Blur my background. Thank you. Ah, this is much better. So now I'm fully operational. Okay, question number 1. Why did the glow stick not glow in the first instance?
Pendulum uno.
You can unmute
That's the
yourself.
first hand up.
Yeah, he can unmute himself.
Because it didn't crack. It didn't crack it.
What didn't I crack it?
Oh, the hydrogen peroxide wasn't released yet.
Okay, awesome. Yes. Right. How many questions do I have to ask? 3 questions. I should ask one of the probability questions, hey? How would that be?
Please give us your number, Bendulo.
Question number 2. Who can remember the name or the glaze that was used?
Thea, can you hear Dr. T?
So I can't hear.
No. Also.
No. Okay, I think they just lost connection. They are back.
Oh yeah, they are back.
Okay, Sneh and Tanya, please unmute yourself. You dropped for 1 minute.
Am I? Okay, thank you. Right. Do we have a taker? No, we don't have a taker.
You didn't hear the question.
Oh, sorry. Okay, I thought, okay, oh, let me just sit. Oh, that's nice. Okay, so the question is, for the, you know, the effect that, what is the name of the effect when you change, when you use heat and the color changes? What is the name of the effect? Remember the first one with the mug? Can somebody remember?
Okay, Pendula, no, we cannot take your hand, Pendula. So Kian, please mute yourself.
Kian? I can't hear you.
Yeah, Kian, please unmute yourself. Okay, let's go to the second
The
hand. one.
photochromic effect.
Okay, there we go.
Say again?
The photochromic effect.
No. But you're close, you're close.
Too close. Let's try the next person, Myla.
Myla, you want to unmute yourself?
Myla, please unmute yourself and then give us the answer.
Myla, you have 3, 2, 1 seconds left to unmute yourself. Otherwise, with the next person, we're going to ask the next person. Myla?
Okay, we go to the next person, Yashoda Governor. Yashoda, please unmute yourself.
No.
They're saying they cannot unmute.
Oh, okay. Okay, Myla, then we're gonna, okay.
Myla, okay.
Myla, did you have the same problem? Myla, you're online now.
Oh yeah,
I
Myla,
think
Yeah,
thermochromic.
exactly. Thermal from temperature. That is correct. Thank you.
okay, Myla, please give us your number via the chat box.
And now I have to think about the third one.
Third one, the last one.
Hey, it's Friday afternoon. What is the last one?
Did you just run? Did you just run from the Aztec down to SNES office?
Exactly. Because we also lost connectivity, so I thought I gotta just do a mad dash.
You lost
by that time, my brain was kind of empty.
Yeah, you lost the question connection.
Yes. I know. I don't know what happened. Okay. So last question is, what is the name of the glow in the dark effect? Myla, you can lower your hand because you've already on the. What is the name of the glow in the dark effect? It's not fluorescence. And there's no taker. Eesh. Okay, no taker, all right. Then we're gonna come back. Okay. What happens when I put a glow stick in hot water?
Yeah, shoulder.
Oh, okay, I think I'll have to unmute you. Yes.
The glow stick gets brighter because the hot water speeds up the chemical reaction.
Fantastic. I couldn't have said it better. You want to start working for me, huh?
She must be employed at Aztec.
Yeah, exactly. Nice explanation. Okay, thank you.
Thanks, Yashoda. Please also give me your number via the chat box. So we had our winners was Yashoda and let me just remember. Myla, and what was the who was the third one? Pendulo.
Pendulo, yes.
Yes. So Pendulo, Myla, and Yashoda, please type your numbers via the chat box. Right.
Okay. Yeah, this is it from my side. I have to go back to work.
Thanks, Tanya.
Rush across again to the street. So as I said, you're more than welcome to visit the Science Centre. Just drop us an email at stec@ukzn.ac.za and hope to see you there. All right. Cheers. I'm going to hand over to Snake.
Okay. Thanks, Tanya. There, you're back.
I'm back.
Do you need anything from me?
Maybe some closing remarks. Yeah,
Okay.
our last day.
Yeah, most definitely. Thanks. First and foremost, thanks to all the learners who participated in this year's TTN. Thanks to Sneh and her team, Leena. Thanks to everybody who did science shows, Tanya, and all the other sectors that did science shows. Thanks to everybody who was doing our chat box, Siyabonga and the rest, the team, Dr. Skosana. Thank you very much. And thanks to all our teachers who just dedicated their time to just come and teach. So that's it from my end. Let's just see each other next year. If you're doing matric, I hope to see you at a university next year. And if you're doing grade 11 or lower, I hope to see you in the next year's TTN. We are going to communicate the details in due time. So thanks from me, Dr. Mthethwa. Thank you guys. Thank you all.
And we will be sharing all the notes and the recordings from Monday, yeah. Sometime next week, we will be sharing them.
Yeah, the notes, all the content will be shared with you, as Sneh said, from Monday. All the notes, all the videos that were recorded while teachers were teaching. If you want to go and revise and study on your own, you'll be free to do so. Just be patient with Sneh. She's doing all that, and she's gonna email everybody all that. Thanks, guys.